So that's the improvement we did on Solayer chain, Infinity SVM, we call that. And another thing is that we have, more ability to customize things. For example,
Hi, I'm Shane. I'm a research partner at Hack VC, and I'm joined today by Chi from Solayer. So, Chi, do you want to introduce yourself?
hi everyone, my name is Chi. I'm an engineer at Solayer Labs. Currently, we're building a L1 SVM based chain, which aims to be fast. And in this session, we will talk why it is so fast.
Okay, awesome. Do you want to kind of start with like the basics? Kind of what is a blockchain, what is EVM, and then kind of go into like SVM and your guys' product?
Yeah. So since we're going to explain why our chain is fast, maybe let's go from the very beginning. So about a blockchain. So a blockchain is basically a software with a state. It's a state machine where you store basically a lot of data. Like in blockchain, it's your balance, and in EVM there are other data in this machine. Um, so it's gonna be like this. Let's say it has $10 here, $20 here, $5 here. Okay. Then in this state machine, there is this global state where everyone sees this state and operate on this state. And in our very early stage of this kind of state machine, you have this one global state where everyone operates on it. So when you have a transaction, say the state machine wants to process it, and then it will read the transaction, parse the transaction, do what the transaction says, and do some operations on it, say +5, -5 here. And then there's another transaction goes in, and it will do some other math. So that is a very simple form of blockchain. And and for EVM, which is like what they described, the world's computer, they will do some additional things on it. They have some more complicated concepts on top of that, which is a virtual machine. So a virtual machine is like, you can think of like a PC, but with very limited capabilities. On top of adding and subtracting balances there, it can add some more complex operations. For example, you can compare or execute some code, like special code, on top of this virtual machine. And the thing about EVM is that it still is this in this simple term of state machine. So in EVM, there are like more state onto this simple form. Maybe like more than balances, there might be data there. Say there's a hex 0, 1 here, maybe indicating some data. Maybe it's your age, not so 1, but it can indicate your age or other types of data. And that's basically how smart contract works. They read data from this state machine, this global state, and they do operations not only on the balances but also on other data. So these data they can represent anything. So that's how like EVM or other types of virtual machine works. They still takes a feed of transactions, a sequence of transactions, and then execute them. So the problem about EVM was like a very early state machine. So Vitalik, they didn't think a lot about parallelism. So these sequence of transactions must be executed sequentially, meaning that transaction one must followed by transaction 2, must followed by transaction 3, no matter of what. Like even transaction 1 is only related to the first 2 accounts, and transaction 2 is only related to the third and the fourth account. They must be executed sequentially. This is like pretty obvious, right? You cannot do them in parallel because it can cause to some problems like double spend or like state inconsistency. If transaction 1 is related to account 1 and account 2, and transaction 2 is also related to account 1 and account 2, if they, execute in parallel, say like this, there is a non-deterministic sequence of these 2 transactions. If both of them, like, they will subtract account 1's balance by 5, and but actually not 5. Let's do 10. If we execute them sequentially, the first transaction will go through, and the balance will be like it'll be here. It's gonna be 5, and the second transaction will fail because you want to subtract 10 you want to subtract 5 by 10. So the second transaction will fail. But if you do the in parallel, maybe it's like when you're doing this subtraction, the state is not updated promptly, and you may have caused some double spend problem. So this is basically a double spend, and in computer science we also call it a race condition, where you the proper way of doing it is you acquire the lock of the global state. You can only do one operation on one state at one time, and give the lock to other ones to still operate on this machine.
But in theory, you could find non-overlapping transactions and do them in parallel, but it's just kind of hard in the EVM, right?
Yes. So that's actually the model designed by EVM. It does not require you to tell the machine whose account you want to access. That causes that you can only know whose account you are going to use at runtime or at execution. That's the main, it's not in the EVM's design to execute in parallel.
Yeah. Cool.
So this is the problem of EVM. Well, it wasn't a problem like years ago because there's no such huge traffic about parallelism, and it's enough to have it simple to keep it single-threaded, sequential execution. But we're now in 2025, and there are tons of transactions. We want to know, we want to improve that. And the method of improvement, as already described here, is that if transaction 1 it access only, if it access account 1 only, and account 1 and account 2 only, and if transaction 2 access account 3 and 4, in theory they can not in theory, but in practically they can execute in parallel because they don't even mess with each other. You don't care about the order of transaction 1 or transaction 2 as long as they execute and no other transactions mess up with account 1 to 4. That's the concept of parallelism. And instead of having this global state machine, we kind of split this global state to a more granular state. So you split all these states to smaller states, and that transaction can access on. So that will to access that, to achieve that, you need to tell the machine before execution or before do the real math, do the real operation, you have to tell the machine what account you want to have access on. And that's like, if you have ever programmed on Solana, you have to, include your account info in your transaction. And that's the reason of that, to increase parallelism. I think that's pretty much about like EVM's parallelism problem. So we can continue to SVM and see how SVM does it. Well, I think there are like, two things makes SVM fast, and this is one of them, and there's another one I'll talk later. So in SVM, this is exactly how Agave or Solana's validator does it. Is that they have a central, this is called the scheduler. This is a central scheduler. And like I said, we can execute in parallel. So we have workers. Worker 1. Worker 2 and worker 3. And then when a transaction comes through, the scheduler will decide whether we can put this transaction into execution. So these workers, they are constantly like, receiving and executing transactions. It's a loop. So when we hit a transaction, when we have a transaction for the scheduler will first see what account does it have. If this account is in use by some worker, say, well, actually, let's just pretend this there's no transaction in the working queue now. So this transaction 1, will be put to some worker, say worker 2, tx1, and this transaction is now in execution, and we will the scheduler will lock the accounts for this transaction. Let's call it 1. So account 1 is now locked, and the scheduler, when it sees next transaction 2, and the transaction 2 has the metadata saying that which accounts I want to have access to. Let's say X account 2, and the scheduler will see that account 2 is now free of use. We can just give you to any worker, maybe some empty worker, because it will be faster. We'll just give this transaction 2 to here, and we will lock account 2. Now we have two transactions executing in parallel, because they don't affect each other. They don't read each other's accounts. And when transaction 1 is done executing, we will unlock the access to account 1. And if another transaction comes through and say transaction 3 with it wants access to both account 1 and account 2. So there's no transaction in worker 2. So the scheduler will say that, okay, so since account 1, you can have the lock of this account. And since account 2 is in use, we may put you after transaction 2, because this would not mess up with account sequence again. It's like how we did in the very simple form of EVM. This is sequential. Even though they both accessed account 2, it doesn't matter because it's safe to do so. And if there is a, say here, we have another transaction 4, it wants access to account 1, account 2, and account 3. Well, it still can be put behind this transaction 3, but sometimes we have to differentiate the read lock and the write lock. Okay, so you may have another question. So if every transaction is trying to access the same account, say you're trying to access a swap that's really popular, isn't it going to be the same model as EVM does? Because you will end up like putting all the transactions in one worker, and it's going to be just single threaded, right? So we want to introduce a concept of read-write lock. So basically, when we have, we don't really need to put transaction 2 and transaction 3, these sequential like we have here. Not necessarily, because if you only want to read the state of account 2, and you only want to read the state of account 2 in like both transactions, you can do that in parallel too, because it's gonna no one's gonna change the data of that, so we are guaranteed that the data is not going to be polluted or what. So this introduced a concept of read lock and the concept of write lock. So a very good example of read lock is the program account. So program. Once you deployed a program, it's going to be binary. It contains all the bytecode and the execution data that's presumably to be immutable like across its lifetime. It's not going to be altered anyways, and you can just read them in parallel in all sorts of matters. And if we have okay, let me now draw another example.
I mean, it could be updated if it's upgradable, and in that case, you'll have some contention just for one transaction.
Yeah, you can like sometimes you can discard the upgrade authority, but yeah. And let's draw this example. Say we have account, this is tx1 with account 1, let's call it read lock, and we have this tx2 with account 1 read lock. And here comes the third account, the third transaction, with account 1 write lock. So it wants to write the data of account 1. But here, simultaneously there are two transactions, 1 and 2, accessing account 1, reading them. You can't really be sure that where should I put transaction 3 to make all these transactions, safe, right? So if you put it here in sequential, like after transaction 2, it could be like since they're in parallel, there is in parallel means that they do not care about the order of the transactions, but it could be transaction 1 after transaction 2 or transaction 2 after transaction 1 because of the execution time. Maybe transaction 2 is shorter and transaction 1 is longer, so the execution time will be different. So if you put transaction 3 after transaction 2, it could be that when transaction 1 is still executing, transaction 2 is done executing, and you're executing transaction 3. So that goes back to the bug again. Here's the race condition. Transaction 3 is trying to write some data while others are trying to read the data, so the data can be dirty or unexpectedly polluted. So this time we cannot really schedule this transaction 3 into any worker because you don't know the deterministic order of these transactions. You have to wait for both transaction 1 and transaction 2 finish their execution and release the lock of account 1 so that transaction 3 can safely write to the account. Does that make sense?
Mm-hmm.
Okay, cool. Then I guess we're pretty that's pretty much about Solana's scheduler, and yeah. So there are some smarter algorithms to detect that Say if you have transaction, in this case, you have transaction 1, 2, 3, all coming at once. Maybe the scheduler is smart enough to say that maybe transaction 3 should go through first, and then transaction 1 and 2, maybe that will accelerate the execution, or maybe some sort of certain ordering will make the sequence, or the validator, the max fee they can get. That's per the scheduling algorithm. But yeah, this is the most basic and the currently Solana's in use scheduling algorithm we have here. This read write lock account here. Okay, so that's one key point of Solana being so fast, or SVM, Solana's virtual machine being so fast. And another one is more on the architecture side. It's the execution model. So this is about the transaction level thing, and on a execution runtime thing, we have two new concepts. So we constantly said is saying EVM or SVM. So the VM stands for virtual machine. And it's basically a computer inside a computer. Well, say your browser is a virtual machine because it also runs code on top of your PC. Your PC is also on top of some even low level sort of code. And EVM and SVM, they are just like that. They're just programs interpreting their own designed bytecode. And these are a little bit different from the very fundamental code that runs on your computers, zeros and ones. These bytecode are on top of an abstraction. And for EVM, it's called the bytecode is called EVM bytecode, and for SVM it's called eBPF. It's it's a type of bytecode that was designed long time ago for kernel modules. Kernel means your operating system, very low level things. And Solana's folks, they ported this to SVM because I think one major issue is the security. We can verify eBPF before executing. We want to make sure that the bytecode itself will not harm the PC or do some unwanted things. It's easy to verify. Let's give it a star. So easy to verify. And the second thing is the speed. So since they are both bytecode, why is eBPF way faster than EVM? This is because eBPF has there's a thing called just in time compilation. So bytecode, as I explained before, it's you can think of a computer built on top of a computer. That will introduce performance issues for sure, because you're basically trying to mimic what the underlying layer wants to do in the faster way. If you want a virtual machine of your say Windows machine, you're basically mimicking the CPU's behavior on top of a software. That will introduce hardware the performance downgrade for sure. And in this case, it's also the same. For EVM, we have this so-called interpreter. So for each bytecode, the program will read the bytecode and decide what it's gonna do in a lot of CPU cycles. But for SVM, since we're using the legacy of a kernel module, we have this just-in-time compiler, or in short, it's called JIT. So it will convert this eBPF bytecode to your machine's bytecode, which is x86 machine code, which eliminates thousands or even tens of thousands times of overhead, and that's another reason to make this really fast. And if you want to to check out the real implementation of this, you can go to, if I remember correctly, it's and I think it's Anza/SBPF. This is a GitHub repo you can refer to. You can see how they converted this bytecode into machine code, which is really fast for that. And I think that's the 2 points on a execution level, runtime level, and also on the transaction level, the scheduling algorithm makes SVM so fast. And okay, any questions about these parts?
No, I think that's clear. Those are the 2 things that you said were the main differences in terms of speed, at least.
Okay, cool. Okay, so after talking about why SVM is so fast, we now want to talk about why SVM is slow in some terms. So you may have heard of like Solana's consensus. It's called something proof of history. So what is proof of history? Solana is not a very centralized chain. Well, actually, it is decentralized. But how do you guarantee that each validator is doing their job correctly and non-maliciously? So we have to it's an algorithm called proof of history plus proof of stake. Proof of stake, just gonna quickly mention it. It's basically, as a validator who built these blocks, packs your transactions, you want to make sure that they do not do something evil. They do not alter your transaction or something like that. You, as the validator, or as the block proposer, you have to put some money in order to be qualified to produce these blocks. And if anyone proves that if you did something wrong, you'll be punished for your funds are just basically gone, and that's the proof of stake part. And Solana has this proof of history. Is that it's something very related to Solana's architecture. In Solana, every leader, or when it's your turn to produce the block, you have limited of time. But what if you say, when it's my turn, I'm gonna delay really, really hard. I'm not going to produce my block until maybe an hour, so that I can receive a lot of transactions and I can choose from the most valuable ones to include in the block. But this is not gonna work because of this proof of history. Proof of history is basically you're constantly doing a mathematics to compute the hash of the current state. This allows you, so in Solana, the slot time is around 400 milliseconds. So let's say you have to do, say 100K. This is just an arbitrary number of hashes. Okay, so say if you have to do 100K of times of hashes, this is a mathematical function you have to spend some time to work on. It's kind of like proof of work. You have to prove that these number of times that you computed these hashes. So in order to do these hashes, you have to again lock the state. And locking means like time consuming, because when you're locking, it means some other people or other components of the system is waiting, and that consumes a lot of time. And that's the major drawback of proof of history. Every not every, but lots of operations you do in your validator will require this lock. And when they're competing for these resources, it's gonna be slow. And that's why Solana wasn't so fast until recent upgrade of they have
Well,
this.
I guess first, how does this hashing solve that issue of a validator waiting an hour to produce its block?
Well, let me think. How can I explain it in a simple way? So okay, maybe let's still use graph to like illustrate this. So for a validator, let's say you have a validator A, validator B, validator C, and there are 3 servers. And the assigned slot, say the network had a consensus that validator A should be producing block 10, validator B should be producing block 11, and validator C should produce block 12. And the network expect every block have 400 milliseconds. But in reality, there can be network delays, or sometimes your computer just works slow for a little amount of time. It cannot be this precise, so it's going to be approximate 400 millisecond, where you have a certain number of hashes. But let's say validator A finish his block 10, and now it's validator B. Validator B can maliciously say that, well, my computer just lagged, so I need more time to process on that. Can the network just hold it for me? Just wait for me. And if without this, proof of history, there's no proof that your PC is being slow. And with this proof of history, everyone else will simultaneously say that validator A will constantly doing the hashes, while validator B should be producing their blocks. So they did 100K times of hashing, and validator C simultaneously did also 100K times of hashing. And the network agreed that we all did the hashing, nothing is wrong, and validator B didn't send us any data. So we're gonna just skip validator B. But if there say it's a real lag, and there is a validator, if there's other validators that there's a validator D, val D, and val E, maybe val F as well. And let's assume validator B just didn't get good connection to validator A and validator C, but he was able to broadcast what he proposed, the slot, to other validators, and they did some proof of history as well. They did some hashes, and they confirmed that their hashing matches, so this quorum matches, and it's a real connection error to validator A and validator C, but the entire network has confirmed that validator B did send us the proof that he had done his work producing the block, and that's basically how we prevent this. Hope it makes sense.
Mm-hmm.
Okay, cool. So that's proof of history. The why we use it and why it slows down the network. So after that, we have something new called OpenGlow. So output glow basically remove proof of history. Remove proof of history. So it says like we don't need this hashing anymore. And we don't need to wait for these locks anymore. If there's again to our validator. Oh, maybe like before that. Okay. I need to add something onto the previous page. Before we move on to the OpenFlow algorithm, the new consensus mechanism, I might need to introduce another term here. It's about finality. So in the previous page, like we have 6 validators, and we have C broadcasting. So this should be broadcasting to 3 of the network, and A and C, they did not receive the broadcast for some reason, network issue maybe. So we now have a 4 nodes in this network out of 6 has confirmed that validator B is giving the correct version of the chain, and that is called a confirmed state. But in order to let the entire network to agree on the current world state of the network, we need to let everyone to trust that this is our agreed state. So we preferably want to get 100% of vote. So after E, F, G has seen and verified these states, they will vote, append their vote onto a Solana block, and these vote verifies that these blocks are valid, and that takes time. Currently, Solana's finalization time. So this is confirmed. This is called finalized. This is not exactly how Solana defines the state, but you can think of it this way. So, in reality, you have to wait for 32 blocks to be confirmed, for a block to be confirmed. Like when you have confirmed block, and then there are 32 more blocks confirmed, this block is considered as finalized. And the time for that, time of finality, is around 12 seconds. That means in this 12 second, anything can happen to the chain state. You cannot blindly trust that the chain is unaltered, not going to be changed forever. But in reality, there has no incident of reverting the chain so far. So when you're developing, you can just assume it's fine. But in reality, or theoretically, there are this around 12-second finality time. And that introduces another new consensus algorithm called OpenGlow. Basically, that removes proof of history. So it says instead of do hashing and vote everything onto the block, we just do a off chain, or it's gonna be on chain but off the block voting. So in the previous regime, you have a block. There are transactions, two types of transactions. One is normal transactions. One is for votes. So we have to wait for the votes to be done to say that this block is confirmed or finalized. But now we are putting the votes off the block, but put it into a, it's something in parallel with the block. they don't affect each other, but it's in the network. But it's not the block you would normally expect. Only contains like user transactions. So we separate the votes with transactions, and that is OpenGlow. And in this case, you don't need to compute hashes. Remember, we have hashes of proof of history, where you have, when you execute the transaction, you have to compute the current hash, the hash of the current state, so that will lock the, the state or your processor unit for some time. And now, since we do not need this, we can just execute them without waiting for anything, and that increases the throughput of the entire network, and that will also eliminate the waiting time of these votes, because now we don't need that many of votes to make a block to be finalized. And there are some security concerns. Basically, the concern is that we sacrifice some security assumption. We assume that we have a lower threshold of security, but because of the economics, if you want to attack this network, you have to pay a lot more than the network itself worth is. So it will be uneconomical. So that's why Anza folks or Solana folks, they want to introduce this to reduce the finality time to, I think, around 1 or 2 seconds, something like that, a lot lower than the 12 seconds we have now. And by the way, like 12 seconds is also, I cannot remember the exact time of proof of history finality time, but 12 seconds is the finality time of Ethereum too, because how they defined a block is a 12-second interval. So once a block, you have to wait for 12 seconds for a block to be produced on Ethereum. And yeah, this new algorithm basically it's kind of a marketing thing for them to beat Ethereum. Okay, so I think that's pretty much about OpenGlow. Any questions in these?
No. So maybe you can start talking about Solayer.
Yeah. Okay. So, so some background first. We started Solayer, building our chain in January, and back then we don't know anything about this OpenGlow, and we wanted to build a faster chain than Solana, and we tried, and then we start to do some profiling, and it turns out the most time-consuming thing is proof of history. We wanted to modify Agave, Solana's current validator, but it turns out with this proof of history on, we cannot do much things about it because we have to wait for the logs. So we started to write our own chain based on we have the same execution environment, the SVM part, but we have different consensus on how we order the transactions. That's the scheduling algorithm, all sort of things, to make the logs as little as possible. And one advantage we have is, instead of having those many validators who are trying to produce their own blocks, we have one single sequencer to produce all the blocks, and we have verifiers in the network to prove that we're not doing anything evil, we're not altering state maliciously. And yeah, that's how basically Solayer, our chain, works. And accidentally, I think it was in May, in Breakpoint Solana, they announced their OpenGlow, and turns out they removed the proof of history too, because that's the main bottleneck here. So we're kind of like OpenGlow now. And so that's the improvement we did on Solayer chain, Infinity SVM, we call that. And another thing is that we have more ability to customize things. for example, like it's easy to understand like why we can build lightweighted things than them, because as a big company like that, you have to consider a lot of compatibility, and we're building from scratch, and we can add any feature we want without any concern. And yeah, that's the, I think, advantage I would say we have.
Okay, so can you get into the architecture?
Yeah, okay. So we have a single, like, maybe, yeah, let's just draw it here. So we have a single sequencer, and we have all types of verifiers. And a sequencer, like, since it's like hosted on our site, it's gonna be, we spend like tens of thousands US dollars to buy a super powerful machine that can do the scheduling really fast. Because like I draw it before, scheduling, you have one central scheduler because you don't want to mess up with the ordering things. Workers can be parallel, but schedulers must be single core. Like, you have to maintain the lock. You have to tell who can access who. So the scheduler itself must be single core. This is the bottleneck we have. And for Solana, they have concerns about, hardware specs for all validators. They cannot ask every validator to spend tens of thousands of US dollars for a super powerful machine so that the throughput can be improved, but we can do that. And so our current testnet or devnet, our current devnet can reach 300K TPS. And TPS, for your reference, Solana currently the day-to-day normal TPS will be around 1K. That's the real TPS, like excluding the votes. And their peak I think their peak was 100K, but it was like stateless operations. You don't lock anything, and that's how they did so good. But the main constraint for them is that they have to consider everyone. They have to not overflow some other machines, something like that. But we don't have this concern, and we have this central sequencer that can achieve 300K at the moment. We're achieving more, hopefully. And to make the state, make everyone to trust the state, we have verifiers. They verify a portion of the transactions. Say if we have a huge block of 300K transactions, or actually let's say just say 300K transactions here, and a verifier which will be expected to be run by a normal user or some validator, they should just run it on the reasonable machine, and they only verify a part of the, say, 10% of the block, and another verifier will verify the other 10% of the block, and so on and so on. So in this way, we can verify that our block is correct and safe. And that's how that's how our consensus works. And we also have the sequencer. So as a user, you can also, more than verify, you can run RPC nodes.
Well, so how does it verify just 10% of the block? Does it have like incremental state?
Yeah, so we when we're publishing the block, we will also publish the account changes of the block. So if you
of every single transaction
of every batches of transaction. So
okay.
if you are the second 10% of the block, you will receive the first 10% of the state changes, and then you will start verifying from that.
Each verifier has to have the entire state of the block, right?
Correct. Yeah, we'll also like include the entire blockchain for them to verify.
So if you are the verifier that's responsible for the, 70 to 80% segment of the block, you have the state at the start of the block, you apply the next 7 quote unquote state changes between each entry.
Yes.
Then you actually literally execute your segment, and then you verify that the state changes that were at the end of your segment match what you actually computed.
There are two ways of verifying that. So basically, there are two modes actually. So one mode is that if you have a block with state changes, say this is assigned, and you also have you have this state change. You can compare with the rest of the state, and you also have this final state. So there are two modes so you can verify that. And you also you have the state of this.
Well, you don't have the state. You have basically the state at the start of the block.
You have the state change. Like that all the counts change. Like you don't care about the transactions inside. You don't care about it. So you only care about the state change. What happened? What happened?
Yeah, but the verifier has to know the state at the start of the block of every account.
Yes.
Then it applies the state change of the transactions at the top, because it doesn't have to execute them because it just gets the account delta change.
Yes.
Right? Then it actually executes the transactions that are in quote unquote assigned, and it ensures that the state change that it computes is what it was given.
Correct. Yeah.
Okay.
Yeah. Let's go back to the RPC side. So as a user, you can also run RPCs. Also one more thing on top of the verifier. Basically, verifiers are validators and how people can participate in this network and get rewards. If you we haven't really decided how we are going to distribute the rewards, but maybe if you have we haven't decided this part yet. But one thought we have is one thought we had here is that if you have a more powerful machine, you may be assigned to more jobs, and also, the job count may also depends on how you behave in the past, and with more verified jobs you have done, you may get more rewards on that, and that's one way user can participate in our network. And the other there's another component of the entire architecture is the RPC nodes. And since sequencer, we want to keep sequencer as small as possible, and we don't want them to handling all the indexing stuff or RPC requests, because RPC requests, they require again the lock of the global state again. So we will distribute these methods, the RPC nodes, to all the RPC capability to the so-called RPC nodes, and it will be. Well, I think they can be put beside the verifier. The verifier itself can act as the RPC node again as well, but there are two components in the same binary. These RPC nodes, they will also receive these blocks from them, and yeah, that's basically how they communicate with each other, and we will have this fan out architecture so that the RPC and the verifier nodes will broadcast all the transactions to the network. And yeah, that's the general structure of our chain.
Mm-hmm. Which allows the RPCs to just not actually execute transactions, but apply state deltas, which does not exist in Solana.
Yeah, if you want to, say, run a very minimal RPC and you want to trust some sources, you can just do that.
Yeah. And so if the verifier sees an issue, then what happens?
Well, hopefully not, because if it does, it means our secrecy is taken down. Maybe, well, it cannot be hacked, but maybe some malicious things happen. Someone altered the traffic. But if the verifier finds something malicious, it will, communicate with other verifiers in the network, and they will, if there is indeed a, disturbing circumstances happened, the entire network will kick off this sequencer. This is we call it a mega sequencer, and it will vote another sequencer. And this voting is going to happen on Solana. Well, theoretically, we're not an L1, but since we're SVM based, we thought it would be good for voting on Solana. And another, we will have partners to run machines to replace us.
And so will the verifiers each put up some sort of stake?
Yes.
Okay. So the sequencer itself doesn't have any stake or notion of stake. I mean, it might in the future if you allow for multiple, or if, like you said, the sequencer gets kicked off and another one gets run, you kind of want to penalize it for having been malicious.
Yes, correct.
So there will be a proof of stake system amongst the verifiers, and anyone can be a verifier.
There's going to be proof of stake, yes.
Okay.
And also, one thing I forgot to mention is that to avoid that verifiers to just blindly voting yes for the block, we will also add some challenges to them. That's kind of proof of work for them to vote no. And yeah.
Mm-hmm. Yeah. Cool. And then, so you mentioned that major improvement of SVM on EVM was eBPF and like JIT and everything. Does that layer in as well, or is that kind of just used by you guys?
Yeah. So that part is so Solana is like a whole unit, and SVM is a part of that, and we're using the SVM. And very gracefully that they have made SVM port very easy, and we can just use their execution runtime, and that's the advantage we have taken from Solana.
Mm-hmm. And so from like a user perspective, the confirmation of your transaction basically comes after your transaction was included in a block. So it's, yeah. Do you want to elaborate on that?
As soon as our mega sequencers pushes the stream to RPC or verifiers, it is considered confirmed, because we don't it's kind of like Solana, where when you push out the streams, it's basically confirmed, and then we wait for finalization. But since the advantage we have compared to Solana is that these verifiers do very minimal job, and that will be a lot faster than that. But since the new consensus algorithm Solana has proposed, I assume that they're pretty competitive too. But yeah, and another thing user can feel is that I think the main thing is still the scheduler. So if you're a developer on Solana, if you have deployed the contract on Solana, you'll need to send hundreds of transactions to the chain, and then do a final click to real deploy the program. And that hundreds of transactions, they're usually untipped, not to Jitto, or just to the network, and they're very low prioritized because they're just doesn't value anything, and you will fail a lot of transactions still today. So I think that's one thing user can experience, and also I feel like Solana's user now don't really feel any friction on swapping or other things, but this is even better for we don't know, if there are more people using blockchains, I think it will be the effect will be better.
Mm-hmm. And then what about censorship resistance? Because if you guys at your sequencer level or are forced kind of by some entity to censor an address, you will be easy for you guys to do that. But from a user perspective, that might be unideal.
Yeah, that's true.
Is there any way to basically ensure that any user will be able to submit a transaction, even if they're censored.
Yeah, censorship is one big thing, like one major problem we have thought in the beginning. Um, so we have a interface to submit directly from Solana to our chain, and that is like embedded in the verifier's code too as well. Like every verifier, they can connect to Solana's mainnet, and there's a special contract we deploy, which allows user to submit their transaction on Solana's chain and be relayed to this our chain. And say if you submitted a transaction on Solana but not relate to our chain, the verifiers will complain about that, and that's also one component of slashing down our sequencer as well. But so we don't, well, as the organization, maybe since self-speaking, like censorship is not so convincing, but like we don't have the incentive to censor any transaction, and the mechanism for the verifiers is there, and but the cost of this relayer is going to be costly compared to directly submitting transactions to our chain.
Mm-hmm. And then how does bridging work?
Oh, bridging. Oh, that's that's another huge topic. So we have just concluded our Cantina's computation for our bridge. The bridge itself, we modify some of our chain to call special syscalls. Syscalls is basically some bytecode, special bytecode that can execute some special operations on our chain, and that will relay the message from Solana to here.
Okay. And then the same for bridging out?
Yes, correct.
Okay. Anything else that you'd like to cover about your system or that makes it unique? Or any use cases that are only possible here?
I will say like our main goal is still the TPS. In the around like so we launched our test with DevNet in May, and at that time we achieved 100K TPS with mix of transfers and swaps, and these are to compute very heavily compute heavy jobs, and at that time in January we did some research about the TPS of Solana. Some claim that they achieved 1 million, but that's apparently not true because we benched again. So the TPS we aim for is like real TPS with conflicted transactions and real transfers with state changes. And yeah, TPS has always been our number one goal. And currently we have 300K. And for execution, we actually already hit 1 million, but that's something we marketed publicly because we know that if it cannot be run in the real environment, we should not market it. So yeah, TPS is always like the number one goal.
And then how do you think about state growth? Because obviously you have 300,000 transactions a second. There's going to be some crazy state growth, right?
Yeah, so we had this vision that when like more and more people are starting to use our chain, like these types, the TPS is not just only transactions. You can embed any data in the transaction. So with 300K TPS, you would have, if I remember correctly, you would have around 500 megabytes of data transferring. So that means like you can do live streaming or do some real time things on the chain, without like it's just like your network, like plugging a net cable into your computer. We can just do that on our chain. You can stream, you can play games and all sort of things. That's I think that's the implication at high TPS can bring us.
Yeah, but won't you have just massive state growth? Like, let's say just every single transaction adds state to your chain, and your state becomes like 100 TB.
Oh, well, this about the state growth. It's really the real state that grows is the account. So if you don't like if you have 7 billion people on the earth, right? So if there's one account for each person, there will only be like 7 billion people. But like no matter how many transactions they did, like they did 10 transactions a day, 100 transactions a day, but the entire state will be still 7 billion accounts. So the state, the ledger will be huge, yes, but the state will be still reasonable for a verifier or for a server.
Yeah, but like you just said, if there's a video game, I mean, to think that the state of a video game of one person playing it would be much, much, much larger than one account.
Yeah, if you want to stream like data, you can just use one account, right? Like
Yeah, but what's stored in the account, the 7 billion people, if each person stores a megabyte, that's a huge amount of data. Right?
if you like want to do some streaming, like game streaming, or just games like network packets, maybe you can use like one or two accounts for like each of them 1 or 2 megabytes, and that will be enough like for a game, right?
But I mean, 7 billion people times 1 megabyte is 7 petabytes. Do you expect an RPC node to store 7 petabytes?
I think we'll see at that day.
What?
We'll see at that day.
That's it. Okay. Well, I mean, Ethereum is having a state growth problem, and Ethereum is what, I don't know, 10 TPS or something.
I think like I have to advocate a little bit about for Ethereum, because TPS was not their number one goal, because they have this 12-second block time. They're not aiming for TPS.
Well, no. I'm not saying it's bad they have 10 TPS. I'm saying your TPS is 300,000 and their TPS is 10, and they're having a state growth problem. How will you not have a state growth problem?
I believe the current snapshot of Ethereum is only like 1 terabyte.
I mean, only 1 terabyte is not small.
That's pretty small for a server. Like the state growth problem for Ethereum is about their Merkle tree. So basically, every block they produce, they have to store another hash for the entire tree. And how they resolve it is by a Merkle tree, is that they don't preserve the entire tree, but they preserve only the latest tree that can be verified somehow. And that's actually not a problem of Solana based ones, because like for Solana, it only keeps a Merkle tree of a 2-day period. And before that, that's actually a problem. That problem for Solana is that you cannot really execute from Genesis to the current state, because it's gonna be like way slow.
Okay, but you could imagine a malicious actor using your entire 300K TPS, and on each transaction they create new state. Wouldn't that create a state growth problem?
Yeah, that's an economy problem actually. Like if we set the price to a fair one, we'll cover.
Okay, so the answer is you're going to solve that via pricing. So like rent or whatever mechanism you're going to use.
Yes.
Okay. Yeah, because you mentioned at the start that you want the verifiers to run on standard hardware. So a standard verifier is not going to have like 100 terabytes SSD or something. So
that's true. Yeah.
Reasonably careful. Okay. Do you have any concluding thoughts about Solayer and where you guys are headed and whatnot? What you're excited about?
Yeah. So basically, we're pretty excited to see what people can do on our chain with this high TPS, and on DevNet and testnet, I think people can test their thoughts the thoughts we had there, either streaming or gaming or other thoughts we didn't have, freely on the testnet. Yeah, I think it's like until people see it, they do not know what's gonna happen. So we're just want to be as quick as we can. Yeah.
Okay. Thank you so much.
Thank you.